with any zeros for the Riemann zeta function on the vertical line. And you will see how useful lemma 4 is. So we already have used lemma 1 once, but now lemma 4 is. So, one of the things that we will use today is this lemma 4 that we had last time. So, just take the lemma 4. That is, so that f be C2 maybe. Double prime for all x let G of x be in C2 AB satisfy, of course, it's always going to be bounded, but that particular bound I'm going to call as M. It's a continuous function on a closed and bounded set. Now this bound will depend upon that integral from t to 2t that we are doing, so it's going to be a function of t for us. Okay. Let G be non-zero, because I'm going to have to divide by G. Non-zero for all x, for each x. And let f prime divided by G prime have at most q zeros, q distinct zeros. And the claim is the integral from a to b of g of x e to the power I f of x dx is less than or equal to some constant, which I calculated to be this, time the over square root of r, m, and q plus 1. So that's what we have. Okay, so now let's proceed to completion of the proof. Okay, so in the proof, we introduced some functions. So recall within the proof, chi of s was defined to be the function which took zeta s to zeta 1 minus s. And that implies that chi of s was pi to the s minus half gamma 1/2 minus s over 2 divided by gamma s over 2. Okay? And then chi of s, chi of 1 minus s was equal to 1. chi of S bar plus chi of S bar. So these two together yielded chi of half plus IT, chi of half minus IT is equal to 1. So that means chi of absolute value of chi of half plus IT is 1. And then we wrote chi of half plus IT as e to the minus, I put a 2I theta because we're going to look at chi of s to the minus half. And we define z of t to be e to the I theta zeta of half plus it, which means this is chi of half plus it to the minus half zeta of half plus it. So that's the definition of z, okay? And from this, we deduced, so note that z of t by this definition turned out to be pi to the minus it over 2 gamma 1/4 plus it over 2 over gamma 1/4 minus it over 2 to the power of half times zeta half plus it, which we also could write as plus or minus pi to the minus it over 2, and then we put gamma 1/4 plus it, and divide by the absolute value of gamma 1/4 minus it, which is the same as gamma 1/4 plus it. It doesn't matter, right? Times zeta. But we lose by plus or minus when we take the logarithm. I mean, it could be that 2I pi gives you I pi. All right, now the other thing is, so this is equation 5. Also, z of t bar equal to z of t bar, which implies z of t is real for real t. Not only that, the absolute value of z of t is the absolute value of zeta half plus t. So we're going to replace the counted zeros of zeta of I plus half plus it by the counting the zeros of z of t. So instead, counting zeros of zeta half plus it, we count zeros of z of t, which means we count the number of sign changes of z of t. So z of t is real. So this is where we were last time. So now the important observation is, if z of t has only a finite number of zeros, so this is a crucial observation. So we're going to put it here. And this is going to be the crux of our proof with all estimates today. So the crucial observation is, if z of t has only a finite number zeros for real t, then for all large enough capital T, we have the absolute value of integral z of t dt from t to 2t must be the integral of the absolute value of z of t dt from t to 2t. Okay? And we will now show that 7 is false. Is false for each t, so for every t, it's false for t sufficiently large. Alright, so there's always a 0. This is crude, of course. There's always a 0 between 2t and 2t, which means the number of zeros, according to this, is like the logarithm of t, at least the logarithm of t, but actually Hardy later refined the proof to show that the number of zeros is like constant times t. Okay. All right, so this is where we were. And so now I'm going to consider the following contours. All right, consider. So we're going to say suppose not, right? We're going to say suppose Hardy's theorem is false. Then 7 holds for all t greater than t. Okay, so we start with the proof is by contradiction. So now consider the following contour. I'll tell you which is important here and which is not so important in this contour. So 0, 1. We got to choose the point to the right of 1. Okay, so we're going to choose something like this. And then we, of course, have to look at half, the critical line. And so we choose this contour between t and 2t. So this is not to scale. Okay, so this is your it, and this is 2it. So this is my contour. Or, yeah, it doesn't matter. If you do it counterclockwise. So that's the contour C. So the contour C is from half plus it to some point to the right of 1. So we're going to choose it to be 5 quarter plus it. Then we go to 2it. And then we go to half plus 2it. And then come back. So the contour C is given this way. Okay, so the first, we're going to apply Cauchy's theorem, and we'll get an estimate on the integral there by doing the integral on the other 3, bounding them suitably. So one will get a bound, and in another case we'll get, so in one case we'll get an upper bound, in the other case we'll get a lower bound, and therefore the 2 cannot be. So we'll get a lower bound for this, and we'll get an upper bound for that, and then one will be smaller. All right, so now let us look at the first one, by Cauchy's theorem. The integral over the contour of chi of s to the minus half zeta of s is equal to 0. So there is no problem with putting zeta. It's only when you put 1 over zeta you're worried about zeros inside the critical space. You're just looking at zeta. Chi is 0 free. That's why we're able to define chi to a fractional power. Because how do you define a fractional power? It's e to the whatever fraction it is, in this case half, log. Log means the function should not be 0. It's 0 free. Okay. All right. So this is equal to 0. So now I'm going to do the following. Okay. So let's note that. The integral from half plus it to half plus 2it, or maybe the other way about it, let's say, but I'm just going to put absolute value of chi of s to the minus half zeta of s ds is the same as the integral of z of t dt from t to 2t in view of 6. Right? So this is actually this, but now I am utilizing an analytic function. So what we have to do is to evaluate this integral by Cauchy's theorem on the other three sides of C. Okay. So by Cauchy's theorem, the size of the integral on the left in 9 is given by the integral on the other three sides, on the remaining three sides of C. Right? And we will bound each of these integrals suitably. So how do we bound each of these integrals? First, we will need Stirling's formula. So this dominates much of analytic number theory simply because the gamma function plays such a role in the functional equation of the zeta function. And Stirling's formula luckily gives a very accurate estimate for the gamma function. So we will need that. Okay. So this we will need. All right. Stirling's formula. Namely, so I'm going to write down Stirling's formula for you in the form which I want. So Stirling's formula is gamma sigma plus IT is equal to t to the power sigma plus IT minus half e to the power minus pi t over 2 minus IT plus I pi over 2 times sigma minus half times square root of 2 pi, that's the constant, times 1 plus capital O. And this holds sigma greater than or equal to half. Okay. So this is Stirling's formula that I'm going to use. Now, I'm going to give you a value which I spent some time calculating. So it's not like I'm just throwing something and I verified that it is true. So I recommend that you sit and do this calculation during the upcoming long weekend in case you're not entirely sure of my claim. Okay, so but one has to be accurate in this calculation. So what is this calculation? Okay, from Stirling's formula, from 10, and the definition of the chi function, 1. So we can now get an estimate for a chi function. We get, I'm going to write down the value. So this is actually in Chandrasekharan, but he just doesn't give the details. So that's why I sat and calculated the details, and you have to take this as e to the log t, and then t becomes minus t, and then the log will give you I pi over 2, and so on. You have to see what the cancellations are. So that's why I took that page and a half to work out the details. Okay. So this is what we get. Chi of s to the minus half is equal to plus or minus t over 2 pi. And I will tell you what is important here. To the power sigma over 2 minus 1/4. That's important. This is not so important. Plus half IT, not so important. absolute value 1 times e to the power minus it over 2 minus, these are all not important, but this comes out of the exact formula. 1/8 I pi, the square root 2 pi cancels, times 1 plus capital O 1. Okay, so as I said, focus on this. So you could simplify your calculation a little bit to zoom in on the dominating term that we need here, which is t to the power sigma over 2 minus 1/4. All right, so this is to be checked. Okay. Now, that by itself is not enough, right? I mean, we need something about the Riemann-Zeta function on this contour. So, next, we need an estimate for zeta s. But this estimate for zeta s that we're going to get will be sharper than the earlier estimate for zeta s that we obtained. So what is this sharper estimate? It's not going to be sharper than anything we've done before in the half-plane sigma greater than or equal to 1. Okay. So in sigma greater than or equal to 1, we know that zeta s is capital O of log t. By the way, the only problem for you is when you hit 1, but you're not going to hit 1. You are on this rectangle well away from 1. So there is no problem us having it. So if you want, you can put s on the contour, like, so it's completely away from 1. Okay, so that is the same as, well, that implies t to the epsilon for every epsilon greater than 0. You're going to have epsilon here anyway because of the fragment Lindelof that I'm going to use. So the log is not going to be terribly useful. All right, 12. Now what about zeta of it? We use zeta of it is equal to zeta of 1 minus it. We go back to chi. See, we have a precise estimate for chi because chi is given purely in terms of gamma. For gamma, we have the power of Stirling's approximation. So to know zeta of it, we go to zeta of 1 minus it, and we have to divide by the chi function of 1 minus it. Okay? Or maybe 1 plus 1 minus it, maybe 1 plus it, it doesn't matter. Absolute value. Okay. Now, what do we know about the chi function? See, I'm dividing. So this is capital O. This part is log t, right? Now this is chi to the minus 1. So I've got to square this. So when I square this, I ignore this part. I get t to the power sigma minus half. Okay? But sigma is now 1. And I'm dividing. And therefore, I end up with 1 over that is this, with a square. But now sigma is 1. So I will get 1 minus half. T to the 1/2 log t by virtue of 11. I want you to really pay attention to this proof because it's hard analysis. So I have got this is half plus epsilon. You can only go with the epsilon here because that's what Fragment-Lindelof does. So by the Fragment-Lindelof theorem, we have zeta of s, we just have to use the convexity. So it's of size that, actually this is of size that in sigma greater than or equal to 1, completely to the right. So we're not going to do it between this and 1, right? So zeta of s is capital O of e to the power, draw the straight line between the two, and you will end up with 1/2 minus sigma over 2 plus epsilon in for half less than or equal to sigma less than or equal to 1. So do you agree with that? If I draw this, here it is 0. I'm just looking at the exponent. The exponent here is 0. The exponent here is half. So this is half. So the exponent of any sigma, so yeah, it's 0, correct? Now, so you just have to do this. Look at that line. And this is actually true between 0 and 1. But I'm using this only for half because of that rectangle. I mean, you can put 0 here, it doesn't matter. Now, in what way is this superior to your earlier estimate? Remember, very early on in the proof of the Riemann-von formula, you said that if your sigma is like delta, you got an upper bound of capital O of t to the 1 minus delta. If you look up your notes, that's what you get. The 1 minus delta is 1 minus sigma. So now we have achieved an improvement of that exponent by half. So it's 1 minus sigma, I got 1 minus sigma over 2. So just make a remark here. Remark 14. 14 improves an earlier estimate zeta s is capital O t to the 1 minus sigma to 0 less than sigma less than 2. So it improves that earlier estimate. Now I've got 1 minus, but that's a crucial improvement. You will see that we need that. So it's 1 minus sigma over 2, which means on the half line, it's 1/4. Previously we had 1/2, now we have 1/4. So in particular, the absolute value, zeta half plus it, is capital O of t to the 1/4 plus epsilon. So that's what we have proved right now. Okay, so it's t to the 1/4 plus epsilon. All right, so what do we know about chi to the s minus half zeta s? Now I have to combine both. So I've got to get the upper bound on this and the upper bound on that. The upper bound on that is given by this, and the upper bound for the zeta is given, so I'm going to put everything together. So if I put everything together, I get capital O of t to the power 1/2 sigma minus 1/4 plus 1 minus sigma over 2 plus epsilon. That's what I get, right? I get this for half less than or equal to sigma less than or equal to 1. I'm just putting this 1 minus sigma over 2 along with this, that one here. That's all I'm doing. And we get this is equal to capital O of t to the power, just that expression, sigma over 2 minus 1/4, plus the zeta function being capital O of t to the epsilon. And this is for sigma greater than or equal to 1, up to 1/5. So now, we just look at the worst cases of this. What is the extreme case? So the extreme case of this is obtained by putting sigma equal to 5/4 here. And the extreme case of this is obtained by putting sigma equal to 1 here. So in particular. And that's what we need to use. I mean, because we are integrating up to this point beyond. And you'll say, sir, why are we going up to this point beyond? Why can't we stop here? The problem is we are later going to use the Riemann zeta function, and then when we deal with this, and we have to sum the Riemann zeta function as an infinite series, and that sum will work only if I go to the right of 1. So that's where I need to go to the right of 1. So you'll see the proof. Why? Okay, so in particular, chi to the s to the minus half zeta s is equal to capital O of t to the 1/4 plus epsilon in half less than or equal to sigma less than or equal to 1, and capital O of t to the 3/8 plus epsilon in 1 less than or equal to sigma less than or equal to 5. So that's easy. Put sigma equal to 5/4 here. You get 5/8 minus 1/4, 2/8. That's your 3/8. And here it is. So these are the bounds that we're going to be using. Okay. So we'll call this 15. 16 is what we will use. All right. So given 16, we say, so in view of 16, we get the integral over the horizontal portions of C, okay? So the integral over CH, if you call, CH is the horizontal slabs, these two. So the integral of that, of chi of s to the minus half, zeta s ds, is less than t to the 3/8 plus epsilon. Because this is actually bounded, goes from half to 5/4. Okay, so this is capital O. Now, what about on sigma equal to 1/4? So that's going to be a little bit tricky, and that's where I'm going to need my lemma 4. Okay. So with regard to integral of chi of s to the minus half zeta s ds over what? Over s belonging to the contour, but sigma being equal to 5/4. That's the vertical part of that contour. What do we get? Okay, with regard to this is equal to, so now you will see where lemma 4 comes in. So this is equal to the integral from t to 2t, t over 2 pi to the power 3/8. I'm using this. Sigma is 5/4, 5/8 minus this. So t to the power 3/8, but now I have to do it, I'll do it very accurately. Okay, so it's t to the 3/8 plus it over 2. You'll appreciate why we have to pay attention here. It over 2, e to the power minus it